So at this point, I've gone on and on and on about all sorts of vulnerabilities and all sorts of attacks you could perform. Now you might think that I'm simply trying to get you to be this black hat hacker who's only out there to destroy systems and so on. Now of course this would ruin our reputation. So let's not do that. Actually, we're learning about exploits to understand how to avoid making those mistakes and to understand how to defend against those mistakes in general, which is also actually a large part of what we do as VUSec. So this is the last lecture on application security, although there will be also an advanced exploitation techniques lecture later on in the course. And this is about defenses. So here we're going to discuss some solutions that people have thought of that can solve these vulnerabilities. Or more accurately, they don't actually solve the vulnerabilities themselves, but they make it harder for attackers to abuse them. Now in this part on application security, I will actually consider those defenses that are most widely used. And so many of these defenses are pretty much almost universally deployed in practice. There are also other defenses that are more advanced that we will discuss in the advanced part of the course. So, the defenses are techniques that basically intend to make attacks harder. And there are essentially two ways to do it. So the first one is to prevent the program from leaking or corrupting any data. So here we're basically addressing the vulnerability itself. The second one is to make code execution harder. So in this case, we allow the attacker to perform the corruption, but we prevent them from using that to execute code. So in this case, the attacker can still do some stuff, but they don't gain as much control over the program. Now, typically, we use both of them in a complementary way. However, I should note that the first is typically more expensive to deploy and therefore less widely deployed. Whereas the second type of mitigation that only makes code execution harder is generally faster and therefore more broadly deployed. It's important to note that these techniques are typically implemented inside the compiler or to some extent in the operating system. So this is what decides which of the defenses are deployed by default. However, current operating systems and compilers also typically allow some more advanced defenses to be explicitly enabled. This piece of code will be our running example throughout the lecture. So let's take a look if you know how to exploit this program. So please pause the recording now and think of the answer for yourself. Now, the answer will now appear. So the attack is simply to provide a name of more than 80 characters and then override the return address. So what happens in this program? Let's go through it quickly. At the top of the program execution, there's the server, which calls echo in a loop. So we're assuming that we have some kind of server that has a socket connection, and now the echo function will take this socket and perform some operation on it. Now, it uses the welcome string to print to the whoever is on the other end of the socket. So what is it going to do? Well, it's going to perform a memcopy, which copies the welcome string into the reply. Then it sends a string over the socket, this particular one, asking the person on the other end to type their name, and it reads the response from the socket. So this call takes the file descriptor that points to the socket, reads the data coming in from the network, and stores at most 128 bytes of those data in the name buffer. Now the end in this case is not decided by the null terminator, so we can safely send null bytes, but instead whether the socket connection is still open. So if the other side closes the socket prematurely before 128 bytes have been sent, this allows it to send a shorter string. Now next there's another memcopy, and this memcopy copies the name into the reply buffer using len as an offset. So the name buffer already has the string that was here, welcome to our system, And then at the end, the memcopy will add whatever was read from the connection. Finally, it writes this string to the reply. So it's writing the string stored in the reply buffer, and it's sending len plus 64 characters to the other end. Now, the attack, as I mentioned, is to provide a name of more than 80 characters. Why is this? Well, so the read call here reads into the name 128 characters, but we only store 64 characters. So anything over the 64 goes over the end of the name. Going over the end of the name, however, is not enough to perform a full exploitation, where we execute a shell. Because the name is stored here, RBP minus 72, and the return address is stored here, RBP plus 8. So first we need to write 80 characters to get to the return address, and then only afterwards can we actually overwrite the return address itself. Now, let's discuss the first defense, stack canaries. These are pretty old and have been in use by default for quite some time now. This is actually the no stack protector option that we've used before. It disables the canaries to allow a buffer overflow to occur. Now, how do stack canaries work? The idea is to put a local variable between, or to put a value between the local variables and the return address. So the compiler adds the initialization of this value in the function prologue. Now this value is known as a stack protector or a canary. So the idea of the canary is that in the past, miners would often be exposed to toxic fumes that would suddenly appear in the mines. Now what they would do is they would bring a cage with a canary inside. The canary would be more vulnerable to the toxic fumes than the miner was. So if at some point the canary dropped dead, that would be a good reason to quickly get out of the mine. This is exactly how these canaries are also used here. In the function epilogue, the compiler adds a check to see if the canary is dead or it has survived. Now, if the canary is dead, it means that the memory was corrupted, right? And the idea is the canary drops dead before we reach the return address. So even if we can override the return address, we will also corrupt the canary. And before we use the return address to return to the function that called us, we already checked the canary and see that it died. If at that point the canary is gone, it means that we must terminate the program, because otherwise there's a risk of control flow hijacking, which of course we do not want. So then we deliberately crash the program rather than allow the return address to be used in the overwritten form. Now, let's take a look at the program we've seen before and see if we can still exploit it even if stack canaries are enabled. So we have the same program as before, although the stack layout slightly changed. Now here we have the stack canary. Why is the stack canary in this particular location? Well, if it's here, it will protect not only the return address but also the frame pointer. And as we discussed before, corrupting the frame pointer allows you to set up a fake stack and indirectly also replace the return address with another. So we need to protect both for the canary to be effective. Now, if we use the attack we used before, it will definitely override the canary before getting to the return address. So my question to you is, can you think of a way around this? Can you think of a way to exploit this vulnerability without having the canary show that there was something wrong? I'll give you some moment to pause the recording and think about this before I give the answer now. And it's the following. What you can do is perform a buffer overflow into len first. So you overflow just this part and you stop before the canary. Now, you manage to modify the len variable, but you have not overwritten the return address yet. Instead, you wait for this line. And you set up the buffer in such a way that with the length that you just specified, it will actually target the return address directly. So now by using the length to jump over the canary, you can overwrite the return address without corrupting it. Okay, so this is a common way to get away with exploiting stack canaries. You jump over the canary by modifying some index or some pointer. Now, attacks are two attacks basically. The one is jumping over the canary, as I mentioned, so you can use a pointer that you corrupt or some computation of a pointer using an index. There's also another way, which is to override the value of the canary with the correct value. So you need another vulnerability to leak the canary, and afterwards you can just replace it with the very same value. This of course assumes that there are no characters in the canary we cannot produce. So if we have a string-based overflow and there's a 0 byte, then this attack will not work. In other cases where we can write any character and we can leak the canary, we can simply overwrite it with the same value, and there's no way for the program to know that the canary is dead, but we actually taxidermied it, essentially. So those were the stack canaries. Let's move on to the next defense. Data execution prevention. As you all know, in the general model that we use for computer systems, data and code are one and the same. Data is just a general term, and code is a specific type of data that happens to be suitable for execution by the programmer. They reside in the same memory, and there's no obvious difference between them. However, this is of course unsafe. We have been able to use shellcode, which is data that was injected in the program, and execute it as code. So, how can we prevent this from happening? We must mark data pages as non-executable. Well, this requires a particular CPU feature, so modern CPUs implement a no-execute bit. And this allows you to mark particular memory areas as containing no code. And if you then attempt to execute these pages as if they were code, so if you point the instruction pointer to one of these pages, the CPU will fault, telling the operating system that something is wrong here, and the operating system typically raises a signal and or terminates the process. Now this is supported on modern CPUs, and modern operating systems typically always have this enabled. Because the feature costs essentially no performance overhead, yet it adds a significant barrier for attackers. So this is typically implemented as a form of write XOR execute. So write XOR execute is a policy that means that there may not be any memory that is simultaneously writable and executable. So basically there's no reason for a program to have self-modifying code on a modern system. And therefore we can enforce this policy, which means that we provide maximum protection against execution, while at the same time not really inhibiting any important functionality. So we use dep support to prevent any writable memory area from being executable. And this prevents things like shellcode. We can no longer write code to the program and then execute it as an attacker. So now the question, assuming we have both stack canaries and write XOR execute, are we still able to exploit this particular program? And how would we do it? Try to think a moment about the answer. So, obviously the old attack no longer works. We were using shellcode, and shellcode is prevented from being executed. So we need to think of something new. And the new solution is actually not inject any code. This is no longer possible, but instead reuse existing code. So instead of writing a pointer to our own shellcode, we write a pointer to existing code and see if we can use that in a way that would be useful for an attacker. This is what we will discuss now. The attacker can no longer inject code, but they can reuse existing code. Well, so what is the most obvious code to reuse? It's actually the standard C library. So if you write a pointer to a function in the standard C library, the return instruction will actually jump to that library and there execute the code that is there. If we can set up the system such that it provides the right parameters to this call, you can use that to, for example, perform a system call, which would be a great result for an attacker. So if, for example, if you can write the address of the system function to the return address, it will execute the system function rather than return to the shellcode. What we need to do in that case, however, is set up the parameters correctly. So the RDI register must have a pointer to a shell command. If we cannot modify the RDI register as an attacker, which we cannot do directly with the buffer overflow because the RDI register is not itself in memory, we have to think of some other approach. So on 32-bit systems, this was very easy because parameters were on the stack, but now that they're in registers, this attack has gotten a bit more difficult. Instead, a modern attack would be to chain together parts of the code into a new program. So this is actually surprisingly effective. We reuse little pieces of code and together make up a new program that will perform whatever attack the attacker wants to do. Now this is known as return-oriented programming, or ROP, and we'll see a brief explanation in the next slide. This is how return-oriented programming works. What we do is we look throughout the code for so-called gadgets. Now what do these gadgets need to have? Well, they need to perform some kind of useful operation. For example, loading a value into a register, loading a value onto the stack, performing a system call, and so on. And they need to end in a ret instruction. The reason for this is that by using ret instructions, we can retain control. What we put on the stack is a list of addresses that point to the gadgets. And every time a gadget completes execution, we get to the return instruction. And the return instruction reads another pointer from the stack and goes there to execute the next gadget. Now, because of this approach, we can chain together small snippets of code from the original program. And a typical program has so much code in it, especially if you also consider the shared libraries it may be loading, so much code that it's very easy to find enough gadgets that you can generate Turing-complete programs with them. So these gadgets are then linked together in a ROP chain that basically consists of a large list of return addresses to be written onto the stack. Now this effectively becomes a program. The program contains some code, that is the pointers pointing to the different gadgets we want to use, and perhaps also some data. That is things that are popped off the stack by the gadgets, for example, to be loaded into registers. So we can now write a full program in terms of just gadgets. This obviously bypasses the protections like data execution protection, because now we're only reusing code that's already in the program. We do not need to write any code, so write XOR execute is not effective, and the code that's already there is already executable, because it's part of legitimate executions as well. Now that I've shown how to break canaries, as well as how to break non-executable regions, let's see for the next technique to help us out and prevent these nasty ROP attacks. And this technique is known as ASLR, Address Space Layout Randomization. And what it does is it randomizes the memory addresses of the different code regions that are in the process image, such as the code, the data, so the global data, the heap, as well as the stack. Now, ROP critically relied on us knowing where the relevant code actually is, because we need to write pointers to the code in memory on the stack to execute it. Now, ASLR prevents the attacker from finding a code pointer to overwrite or knowing what to overwrite it with. So, this could be an effective defense against ROP chains. Moreover, because the MMU, the memory management unit in the CPU, allows us to easily remap virtual addresses to different physical addresses, it's actually very easy and very efficient to change the location of the code in memory. We only have to make sure that the code does not rely on its virtual location in memory, which we can easily do by enabling a compiler flag that allows the code to be moved. With this compiler flag, we get position-independent code that can be moved around without breaking it. Here we have our vulnerable code again. So let's think about this. If we enable stack canaries, and we enable non-executable memory, and we enable ASLR, can we still exploit this? So let's assume the implementation of ASLR is actually perfect, and we have no way to just guess where in memory the code will be. Let's think about it. Pause the recording until you have the answer. Okay, now I'll give the answer. What you can do is leak a pointer. If you are able to leak a pointer, to the attacker, it means that the attacker can use this pointer to compute the locations of the other stuff. As I mentioned, ASLR moves around code segments, right? Large chunks of code and large chunks of data moved around together. If you find one pointer, you can derive where the section is, and then you have broken ASLR. You can perform your attack as before. Is there any space here where we can leak data? Yes, there is a space. So, we can leak the pointer in the first call to echo by not filling the full name buffer. Right? So if the read does not fill the full name buffer, we get whatever was already in memory at that point. And there will almost certainly be some pointer stored in memory that we can use. Okay? So we leak the pointer after the call to read, which is stored in memory somewhere. And now we critically rely on the fact that there's a loop here. The loop means that after the first attempt, where we leaked the pointer, we can try again. Well, now that we leaked the pointer, we know all the relevant addresses, and we can simply perform the attack as we have done before. ASLR, as I mentioned, is also not foolproof. We can bypass it by leaking the addresses, but we can also do other things. For example, we could leak some code or data, and we can typically still recover the addresses from it, at least the relative addresses, which still helps if we already have some idea of where the code is. Finally, another approach to attack ASLR is to use side channels. So it's actually possible to use subtle timing differences based on microarchitectural behavior to see how the address space is actually laid out. So you perform a lot of operations and you time these operations, and then you can to some extent tell how the address space is laid out. This is especially effective, for example, in exposing the address space layout of the kernel. So these techniques are usable. I will not go into them right now because this is not a course on hardware security, but it does show how hardware behavior can undermine software security, which is interesting in itself. So as I mentioned, one of the core weaknesses of ASLR is that it only randomizes whole sections of the address space, which means that if we know one pointer, we know all of the pointers. So this is known as coarse-grained ASLR, and as the name implies, there's also such a thing as fine-grained ASLR. We will not go into this now, but we will see later that it also has some issues of its own. So it's not a perfect solution either. Another issue is that few of the bits are truly random. So because of the way that the memory is managed, we can actually not use 64 bits to randomize. We have to use only some of the bits. So for example, the 12 lowest order bits indicate where in the page some piece of memory is. We cannot move that. We cannot move things within a memory page based on the way that the CPU organizes memory. So we lose those 12 bits. As we have already seen, the 16 topmost bits are also not used. So we also don't have access to those bits. So we lose a lot of bits, which means that there are fewer possible randomizations, which means that brute forcing becomes easier. On 32-bit, actually, it's almost completely hopeless. There are so few bits available that you cannot really have effective ASLR on 32 bits, unless you assume the attacker never wants to do brute force because they don't want to crash the program. So this is the final slide for the application security lectures. Well, if this has told us anything, it should be that application security is very much a cat and mouse game. So these are only some of the most common attacks. There are more attacks out there, and you can make it as complicated as you want. More complicated vulnerabilities are typically also harder to find, so there are many out there that we don't even know about yet. In fact, it's very likely that organizations like the NSA actually do know about them, but are not telling us. This has certainly happened in the past. So we must assume that programs are vulnerable. We will discuss some of the more advanced attacks, by the way, in the advanced exploitation lecture. Moreover, new attacks are published frequently at conferences. So we know that there are many attacks out there, and we know that it's only getting more. Well, it's also a cat and mouse game, because even though we try to constantly find new defenses, and we definitely do, more defenses will be covered later even. In practice, Only the more basic ones, such as the ones we described here, are deployed in practice. More advanced attacks are typically not used in production environments because they cause too much overhead. And in the end, people care more about performance, which implies money, because of course it costs money to execute code, care more about this than about security. And even so, attackers seem to always find ways to bypass our defenses. So the situation right now is we've basically kicked out most of the script kiddies. It's not trivial to do an attack like the ones we described here on an up-to-date modern system. The bar is getting higher, but we cannot stop a resourceful attacker. In fact, even you guys, now that you've learned these things and given the level you're already at, you're probably able to break most of these things in practice. Of course, you should do this ethically, only with the permission of the person maintaining the system. And you can use this to learn more about these systems, but even you should be able at this point to attack lots and lots of real systems out there that are vulnerable and have either no defenses or defenses that are already broken. So this is a cat and mouse game that we're not going to completely get rid of. Computer security will remain important for the foreseeable future to come.